Palo Alto Prisma Access Introduction. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series we are doing a complete guide to Palo Alto Networks Prisma Access, with a deep focus on routing architecture and the critical challenge of asymmetric routing. This is a topic that trips up many network engineers who are new to cloud-delivered security platforms. Prisma Access is a cloud-delivered security platform built on Palo Alto Networks' next-generation firewall technology. Rather than deploying physical or virtual firewalls at each branch office or in each data center, Prisma Access delivers security as a service from a globally distributed cloud infrastructure. Think of it as consuming Palo Alto's entire security stack option: App ID, User ID, Threat Prevention, URL Filtering, DNS Security, and more from the cloud, without managing the underlying hardware. The platform addresses two primary use cases. First, securing mobile users, meaning remote workers and roaming employees, who connect using the Global Protect agent. Second, securing remote networks such as branch offices, retail locations, and SD-WAN sites that connect via IPsec tunnels. Both use cases funnel traffic through Palo Alto's cloud infrastructure, where security policy is enforced before traffic reaches its destination. The business driver is straightforward. As workloads move to software as a service applications and cloud environments, backhauling all traffic through a central data center firewall is increasingly inefficient and introduces significant latency. Prisma Access allows security to follow the user, enforcing the same policy regardless of whether someone is working from a corporate office, a coffee shop, or a branch in another country. Core Components Deep Dive. Now let us go deeper into each core component of Prisma Access to understand the specific role each plays in the architecture. Panorama is the management plane. All configuration in Prisma Access flows through Panorama using a special plugin called the Prisma Access plugin. This plugin extends Panorama with cloud-specific configuration templates and service infrastructure controls. Panorama communicates with the Palo Alto cloud infrastructure to provision gateways, configure routing, and push security policy. Without Panorama, you cannot configure Prisma Access. It is the mandatory control plane. The Global Protect Gateway is the component that terminates VPN sessions from mobile users. When a user opens their Global Protect agent, it authenticates and connects to the nearest available gateway based on latency and gateway selection algorithm. The gateway establishes an encrypted tunnel, and all of the user's traffic is sent through that tunnel to the gateway, where it is inspected and forwarded. The gateway assigns the user an internal IP address from a configured address pool and applies user-based policy. Remote networks are the mechanism for connecting physical locations. Each branch configures an IPsec tunnel to a designated Prisma Access location. From Palo Alto's perspective, each remote network has a configured set of subnets that are accessible through that tunnel. Routing must be configured to ensure that traffic destined for branch subnets is directed through the correct tunnel. The service connection is arguably the most critical routing component. It is the IPsec or BGP-enabled tunnel connecting Prisma Access back to the corporate headquarters or data center. The service connection defines how Prisma Access reaches internal resources and how the internal network reaches resources in Prisma Access. BGP is typically used over the service connection to exchange routes dynamically between the corporate network and Prisma Access. Finally, the compute location is the Prisma Access terminology for the geographic region or zone where a particular gateway or service connection is deployed. Compute locations correspond to real geographic regions such as US East, US West, Europe West, Asia Pacific, and so on. Choosing the right compute locations is critical for performance and for understanding routing paths. Prisma Access Routing Architecture. Now we reach the heart of this series: understanding how routing works within Prisma Access. This is the foundation you need before we can discuss asymmetric routing problems and their solutions. Prisma Access uses a concept called the service infrastructure to handle routing. Within the service infrastructure, there is an internal routing domain that connects all gateways and service connections within a given compute location. Think of this internal domain as a private virtual backbone that Palo Alto manages on your behalf. Routes within this backbone are automatically propagated between components by Palo Alto, but the routes that enter and exit the backbone are your responsibility to configure correctly. Route exchange in Prisma Access happens at two primary boundaries. The first boundary is the service connection, which connects the Prisma Access backbone to your corporate network. Here, BGP is the preferred protocol for dynamic route exchange. Your corporate router peers with the Prisma Access service connection endpoint and advertises your internal subnets. Prisma Access in turn advertises routes for mobile user IP pools, remote network subnets, and other Prisma-managed prefixes back to your corporate router. The second boundary is the remote network IPsec tunnel. RAWs for subnets at each branch are configured statically during remote network onboarding in Panorama, or they can be learned via BGP if the branch router supports it. These RAWs tell Prisma Access which subnets are reachable through each remote network tunnel. A critical and often misunderstood aspect of Prisma Access routing is that each compute location operates as an independent routing domain. A gateway deployed in US East does not automatically share routes with a gateway deployed in Europe West. If you need cross-region routing, for example, a mobile user connecting to US East who needs to reach a branch connected to Europe West, you must ensure that the necessary routes are propagated through the service connection at the corporate network and re-advertised back into Prisma Access. This cross-region dependency is a major source of routing complexity and a common cause of asymmetric routing. What is asymmetric routing? Before we discuss how asymmetric routing manifests in Prisma Access specifically, let us establish a clear and complete understanding of what asymmetric routing is, why it exists, and why it is a serious problem for stateful firewalls. Asymmetric routing occurs when the forward path of a packet and the return path of the response packet travel through different network devices or different network paths. In a symmetric routing environment, a packet from host A to host B travels through router 1, and the response from host B back to host A also travels through router 1. Both directions of the session flow through the same device. In an asymmetric scenario, the forward packet goes through router 1, but the return packet takes a different path and goes through router 2 instead. For simple layer 3 devices that make independent per packet forwarding decisions, asymmetric routing is generally not a problem. A router does not need to see both directions of a flow. It simply looks at the destination IP and forwards based on its routing table. Each packet is treated independently. The critical problem arises with stateful devices, firewalls and stateful inspection engines. A stateful firewall tracks the complete state of each TCP or UDP session. When a packet initiates a connection, the firewall creates a session table entry recording the source IP, destination IP, source port, destination port, and protocol. All subsequent packets that belong to that session must pass through the same firewall so it can match them to the session table entry and apply policy correctly. If the return traffic for a session takes a different path and arrives at a different firewall instance that has no knowledge of the original session, that firewall will either drop the packet because there is no matching session entry, or it may flag it as an out-of-state packet and generate a security alarm. Either way, the session breaks. TCP connections will stall and eventually time out. UDP-based applications may experience packet loss or complete failure. The end user experiences this as application instability, slow connections, or complete connectivity failure. In Prisma Access, because the security enforcement is done by distributed, stateful, virtualized firewall instances across multiple geographic regions, ensuring that both directions of every session flow through the same enforcement instance is a fundamental architectural requirement that must be carefully planned and maintained. Solutions to asymmetric routing. With a clear understanding of the root causes, Let us now explore the solutions that Prisma Access provides and the design best practices that prevent asymmetric routing from occurring in the first place. The first and most important solution is proper BGP advertisement design. Every prefix that generates return traffic through Prisma Access must be correctly advertised via BGP from the corporate network into Prisma Access. This sounds obvious, but it is frequently misconfigured. Engineers often advertise summary routes that are too broad or too narrow, causing some subnets to not have a return path through Prisma Access. A disciplined approach is to audit every subnet that internal users need to access and verify a corresponding BGP advertisement exists for each. Use specific prefixes rather than overly summarized ones when routing behavior must be deterministic. The second solution is the use of Prisma Access routing preference, which is a feature that allows administrators to define which compute location's service connection should handle traffic from a given set of subnets. By explicitly controlling where traffic enters and exits the service connection, you ensure that both forward and return paths use the same enforcement point. The third solution is traffic steering policy within Prisma Access. Traffic steering policies allow administrators to define rules that match traffic by source, destination, application, or user and direct it to a specific next hop or compute location. This gives fine-grained control over asymmetric path scenarios by forcing specific flows through specific gateways. The fourth solution is symmetric gateway selection for mobile users. By configuring global protect gateway selection policies that are based on the user's source region or identity attributes, you can ensure that users in the same geographic region consistently connect to the same gateway. This consistency prevents a situation where a user's session starts on one gateway but subsequent packets from the server side try to return through a different gateway. The fifth solution is to deploy redundant service connections in multiple compute locations. While this increases cost, it eliminates the cross-region routing dependency that is the root cause of many asymmetric routing scenarios. When each major compute location has its own service connection, traffic from users connected to that region stays within the region's enforcement boundary for its entire journey, eliminating cross-region asymmetry entirely. Traffic steering and policy configuration. Traffic steering in Prisma Access is one of the most powerful tools available to address routing challenges including asymmetric routing. Let us walk through the diagram and understand how traffic steering policy decisions are made. The traffic steering decision process begins when a packet arrives at the Prisma Access service infrastructure. The platform first evaluates whether the destination matches any configured traffic steering rules. These rules are processed in order, and the first matching rule determines the forwarding action. Traffic steering rules are matched based on several attributes. The source zone identifies whether traffic originated from a mobile user, a remote network, or an internal source via the service connection. The destination address identifies the prefix or host the traffic is trying to reach. Applications and services can also be used as match criteria using App ID, which is one of Prisma Access's most powerful differentiators over traditional routing. User and group identity, learned via user ID, can also be used to steer traffic differently based on who is sending it. Once a rule matches, the action defines the forwarding behavior. The action can direct traffic to the internet directly, which is appropriate for software as a service traffic that does not need to traverse the corporate network. The action can direct traffic through the service connection back to the corporate network for internal resources, or the action can direct traffic to a specific remote network if the destination is reachable at a known branch location. From an asymmetric routing perspective, traffic steering is critical because it creates deterministic forwarding decisions. When you define explicit traffic steering rules, you eliminate the ambiguity of relying purely on routing table lookups. A routing table might have multiple equally valid paths to a destination, and different packets in the same session might take different paths based on load balancing or route metric changes. Traffic steering overrides this variability and ensures that all traffic matching a rule always takes the same defined path, which is the fundamental requirement for stateful firewall operation. The best practice is to configure traffic steering rules from most specific to least specific, ending with a default rule that handles all unmatched traffic. Document each rule with a clear description of what it handles and why. Review and audit traffic steering rules whenever new subnets, applications, or remote networks are added to the environment, because new destinations introduced without corresponding traffic steering rules can reintroduce asymmetric routing scenarios. Routing preference configuration. Routing preference is one of Prisma Access's most direct and powerful mechanisms for controlling where traffic enters and exits the service connection, which makes it a primary tool for preventing asymmetric routing. Let us walk through this diagram and understand how routing preference works end-to-end. The routing preference configuration exists at the compute location level within Panorama. Each compute location that has a service connection can be assigned a routing preference that determines which prefixes are associated with that location's enforcement boundary. When a packet arrives at Prisma Access destined for an internal corporate subnet, the routing preference table is consulted to determine which service connection, and therefore which compute location, should handle that traffic. In the diagram, we have two compute locations, US East and Europe West. Each has its own service connection. US East's service connection terminates at the corporate US data center, while Europe West's service connection terminates at the corporate European data center. The routing preference configuration tells Prisma Access that traffic destined for US internal subnets in the 10.1.0.0/16 range should always exit through the US East service connection, and traffic destined for European internal subnets in the 10.2.0.0/16 range should always exit through the Europe West service connection. Without routing preference, Prisma Access would rely purely on the BGP routing table to make this determination. If both service connections advertise both subnet ranges, which can happen when corporate routers redistribute all routes into BGP, then Prisma Access may make inconsistent forwarding decisions based on BGP path attributes, potentially sending traffic out through the wrong service connection and creating an asymmetric return path. With routing preference explicitly configured, the forwarding decision is deterministic regardless of what BGP advertises. This is the critical distinction. Routing preference provides policy-based path control that overrides pure BGP routing table decisions. This determinism is exactly what stateful firewall session tracking requires. Service connection redundancy design. Service connection redundancy is both a high availability requirement and an asymmetric routing consideration. Let us walk through the redundancy design options and understand the routing implications of each. Prisma Access supports up to 2 service connections per compute location. These 2 connections provide active-active or active-passive redundancy for the path between Prisma Access and the corporate LAN. In an active-active configuration, both service connections are operational simultaneously and BGP sessions are established on both. Routes are advertised through both paths, and traffic is distributed across both connections. In an active-passive configuration, one connection is primary and the other becomes active only when the primary fails. From the diagram, the active-active design introduces a specific asymmetric routing risk. If the corporate router distributes incoming traffic across both service connections using ECMP, equal cost multipath, then return traffic for a given session might arrive at Prisma Access through a different service connection than the one that carried the original forward traffic. Since each service connection terminates at a different virtual interface with its own session table, the return traffic arrives at an enforcement instance that has no knowledge of the forward session, and the packet is dropped. The solution for active-active service connections is to use BGP attributes to ensure session stickiness. Specifically, you can use BGP-AS path prepending or local preference to make one connection preferred for specific prefixes while the other connection is preferred for different prefixes. This creates a form of traffic engineering where each prefix group consistently uses the same service connection for both forward and return traffic, maintaining session symmetry. Alternatively, if the corporate network uses a router or firewall that supports stateful NAT. Applying source NAT on traffic entering the service connection can mask the true origin of the traffic and make session tracking independent of which service connection carried the packet. However, NAT introduces its own complexity and is generally considered a workaround rather than a preferred design pattern. Remote Network BGP Design. Remote networks, the branch office IPsec connections, have their own routing considerations that differ significantly from the service connection. Let us examine how BGP is used for remote network routing and the specific asymmetric routing risks that arise from branch connectivity. Remote networks support two routing modes. The first is static routing, where the administrator manually configures the subnet prefixes reachable at each branch in the Panorama remote network configuration. This is simple but inflexible. If subnets at a branch change, the Panorama configuration must be manually updated. The second mode is dynamic routing using BGP, where the branch router peers with the Prisma Access remote network endpoint and advertises its local subnets dynamically. BGP is strongly preferred for any deployment with more than a handful of branches because it scales and adapts automatically. The asymmetric routing risk specific to remote networks occurs when a mobile user at one branch needs to communicate with resources at another branch. Consider the flow. A mobile user at branch A connects via Global Protect to the US East Gateway. The user initiates a connection to a server at branch B, which is connected via remote network also at US East. The forward traffic flows from the mobile user through the gateway into the Prisma Access internal backbone and then out through branch B's remote network tunnel. So far, this is symmetric. The return traffic from the server at branch B must traverse the remote network tunnel back into Prisma Access and then be forwarded back to the mobile user through the US East Gateway. If Prisma Access correctly identifies that the mobile user's IP belongs to the US East Gateway, the return path is symmetric. However, if the mobile user's IP pool prefix is not in the Prisma Access routing table on the remote network side, the return traffic cannot be forwarded and the session breaks. The solution is to ensure that mobile user IP pool prefixes are always present in the Prisma Access routing table accessible from every remote network. This is handled automatically within the same compute location, but for remote networks in different compute locations, explicit cross-region route propagation must be configured. This is done through the Prisma Access infrastructure configuration in Panorama, where cross-compute location route sharing can be enabled for specific prefix groups. Security policy and routing interaction. In Prisma Access, security policy and routing are more tightly coupled than in traditional network architectures. A packet that does not match a security policy allow rule is dropped before it is ever forwarded, even if a valid route exists in the routing table. Understanding this interaction is critical for troubleshooting connectivity issues that may look like routing problems but are actually policy denials. The processing order in Prisma Access follows a specific sequence. First, the packet arrives at the enforcement engine and is matched to a security zone based on the interface or tunnel it arrived on. Second, the routing table is consulted to determine the egress interface and next hop for the destination. This lookup determines the destination zone. Third, the security policy is evaluated using the source zone, destination zone, source IP, destination IP, application identification from app ID, and user identity from user ID. If a matching allow policy is found, the packet is forwarded. If no matching allow policy is found, the packet is dropped and logged. The asymmetric routing connection here is subtle but important. When Prisma Access drops a packet due to policy denial, it logs the drop with the source and destination zone information. Engineers who are not familiar with the Palo Alto policy model sometimes interpret these drops as routing failures and spend time investigating BGP advertisements and routing tables when the real issue is a missing security policy rule. Always check the traffic logs and threat logs in Panorama before investigating the routing table. Conversely, a security policy allow rule that has an incorrect destination zone. For example, A rule that allows mobile user to untrust traffic but does not allow mobile user to trust traffic can cause traffic to the corporate LAN to be dropped even though the routing path is completely correct. The traffic reaches the enforcement engine. The route lookup correctly identifies the service connection as the egress, but the security policy evaluation finds no matching allow rule for mobile user source to trust destination, and the packet is dropped. The best practice is to always create security policies with both the routing architecture and the zone architecture clearly mapped. Document which zones represent which types of traffic, and verify that for every valid routing path in the network, there is a corresponding security policy that permits that traffic. Use the policy optimizer feature in Panorama to identify unused or overly broad rules that may be masking actual connectivity requirements. Panorama Configuration Walkthrough. Let us walk through the actual Panorama configuration steps that are required to properly configure routing in Prisma Access, with emphasis on the settings that directly prevent asymmetric routing. The first configuration block is the service connection setup. In Panorama, navigate to Prisma Access, then Remote Networks and Service Connections, then Service Connections. Click Add to create a new service connection. You give it a name, select the compute location such as US East, and configure the IPsec tunnel parameters including the peer IP address, IKE profile, and IPsec profile. Under the BGP section, enable BGP, set the peer AS number which is your corporate router's ASN, set the local AS number which Palo Alto assigns, and set the peer IP address of your corporate BGP router inside the tunnel. The local preference and route advertisement settings control which prefixes Prisma Access announces to your corporate router. Enable the option to advertise mobile user IP pool prefixes and remote network subnet prefixes so your corporate router receives full routing information. The second configuration block is the routing preference setting. Still under service connections, look for the routing preferences section. Here you define which destination prefixes should be routed through this specific service connection. Add each internal subnet range that is reachable through this specific service connection's corporate network. This creates the deterministic routing policy that overrides BGP table ambiguity and ensures that traffic destined for these prefixes always exits through this specific service connection, providing the symmetric path required for stateful inspection. The third configuration block is the traffic steering policy. Navigate to Prisma Access, then Service Setup, then Traffic Steering. Create rules in order from most specific to most general. Each rule specifies a source zone, destination prefix or application, and an action of either internet, service connection, or a specific remote network. The third configuration block is the traffic steering policy. Navigate to Prisma Access, then Service Setup, then Traffic Steering. Create rules in order from most specific to most general. Each rule specifies a source zone, destination prefix or application, and an action of either internet, service connection, or a specific remote network. The order of rules matters. The first matching rule wins. Place corporate subnet rules before the default internet rule to ensure internal traffic is correctly steered through the service connection rather than being sent directly to the internet. The fourth configuration block is the remote network BGP configuration. Navigate to Prisma Access, then Remote Networks and Service Connections, then Remote Networks. For each branch, click the Routing tab and select BGP. Configure the peer AS of the branch router, the peer IP inside the tunnel, and the local preference for routes received from this branch. Under the Outbound Route Filters section, you can optionally configure prefix filters to control which Prisma Access prefixes are advertised to the branch router. Always advertise the mobile user IP pool prefixes to branch routers so that traffic from branch users to mobile users can be correctly returned through Prisma Access. Design Best Practices Summary. Let us consolidate everything we have covered in this part of the series into a comprehensive set of design best practices. These principles, when applied consistently, will eliminate asymmetric routing from your Prisma Access deployment and ensure stable, predictable session behavior for all users. The first principle is ROT specificity. Always advertise the most specific prefixes possible in Border Gateway Protocol, and avoid using broad summary ROTs unless every subnet within that summary is reachable through the same path. Specific ROTs give Prisma access deterministic forwarding decisions. Summary ROTs create ambiguity that leads to asymmetric paths. This applies to both what the corporate network advertises into Prisma access and what Prisma access advertises back to the corporate network. The second principle is compute location alignment. Keep the service connection, the remote networks, and the primary user population for a given region all within the same compute location where possible. When all three components share the same compute location, routing stays within a single enforcement domain and cross-region asymmetry cannot occur. Only use cross-region routing when geographic constraints make same-region deployment impossible. The third principle is traffic steering first. Always configure explicit traffic steering rules for every class of traffic in your environment before relying on BGP routes alone. Traffic steering creates a deterministic, policy-driven forwarding layer on top of the routing table. Any traffic not covered by a traffic steering rule falls back to routing table decisions, which can be non-deterministic in multi-path environments. The fourth principle is access ROT discipline. In split tunnel deployments, the access ROTs configured in Global Protect must exactly match the prefixes advertised into Prisma access via BGP on the service connection. Any prefix in access ROTs that is not reachable through Prisma access creates a black hole for traffic entering the tunnel. Any prefix reachable through Prisma access that is missing from access ROTs causes traffic to bypass the tunnel and potentially reach internal resources through uncontrolled paths. The fifth principle is continuous monitoring. Asymmetric routing is not always a static condition. It can develop dynamically as BGP ROTs change, as service connections failover, or as new subnets are added without updating routing preference or traffic steering configurations. Implement continuous monitoring of BGP session state, traffic logs, and session drop rates. Set up alarms for sudden increases in policy denied or asymmetric drop events. Treat routing as a living configuration that requires ongoing maintenance, not a one-time setup task. IKE version 2 and IPsec tunnel design for service connections. The service connection and remote network tunnels that carry Prisma access traffic are built on IPsec, and the specific IKE and IPsec parameters you choose directly affect both the security and the stability of the routing that flows through them. A tunnel that flaps, goes up and down repeatedly, causes BGP sessions to restart, routes to be withdrawn and re-advertised, and sessions to break mid-flow. Stable tunnel design is therefore a direct prerequisite for stable routing. IKE version 2 is the mandatory IKE version for Prisma access service connections and remote networks. IKE version 1 is not supported. IKE version 2 is preferred because it is more efficient. It reduces the number of messages required to establish a security association from 9 in IKE version 1 aggressive mode down to 4 in IKE version 2. IKE version 2 also has native support for mobile IKE, which enables the IKE session to survive IP address changes on the client side, which is valuable for remote network connections where the branch's ISP may change the WAN IP address. The IKE Phase 1 parameters define how the two endpoints authenticate each other and negotiate the encryption keys for the IKE control channel. The recommended settings for Prisma access are AES-256 for encryption, SHA-256 or SHA-384 for integrity hashing, and Diffie-Hellman Group 14 or Group 19 for the key exchange. The IKE lifetime should be set to 28,600 seconds, which is 8 hours. Avoid very short IKE lifetimes. A lifetime of 1 hour means the IKE session must be renegotiated every hour, and any disruption during renegotiation will drop the BGP session running inside the tunnel. The IPsec Phase 2 parameters define the encryption for the actual data tunnel. Use AES-256 or AES-GCM-256 for encryption, SHA-256 for integrity, and enable perfect forward secrecy using DH Group 14. The IPsec lifetime should be set to 3600 seconds, which is 1 hour. Enable dead peer detection with an interval of 10 seconds and a retry count of 3. Dead peer detection is the mechanism that detects when the remote endpoint has become unreachable and tears down the tunnel cleanly so that routing protocols can detect the failure and reconverge, rather than leaving a stale tunnel up with no traffic flowing through it. For the service connection specifically, always configure two IPsec tunnels, a primary and a secondary, and use BGP with different local preference values on each to control which is active. The secondary tunnel should be pre-established, not on demand, so that failover is instantaneous and BGP convergence happens quickly. A failover that requires re-establishing the IKE and IPsec phases from scratch can take 30 seconds or more, which is long enough for TCP sessions to time out and for users to experience visible outages. Prisma Access with SD-WAN integration. The integration of Prisma Access with SD-WAN is one of the most powerful and architecturally interesting deployment patterns available today. SD-WAN provides intelligent path selection across multiple WAN links at each branch, while Prisma Access provides cloud-delivered security enforcement. When combined, organizations get both optimal connectivity and consistent security without the need for physical security appliances at every site. In the diagram, the SD-WAN edge device at each branch has multiple WAN links, for example, MPLS, broadband internet, and LTE. The SD-WAN controller determines which WAN link is used for which traffic based on real-time performance metrics like latency, jitter, and packet loss. The SD-WAN device establishes an IPsec tunnel over each WAN link to the Prisma Access remote network endpoint. Prisma Access sees these as separate tunnels from the same branch, each originating from a different source IP. The routing challenge in SD-WAN and Prisma Access integration is ensuring that when the SD-WAN device switches from one WAN link to another, the Prisma Access routing table updates correctly and existing sessions are not disrupted. If the SD-WAN device is running BGP with Prisma Access over each tunnel, the BGP session on the failed WAN link will go down and the session on the surviving link will remain active, and routing will automatically converge to the surviving path. This is the recommended integration model. A critical consideration is the ECMP interaction. If the SD-WAN device sends traffic over two WAN links simultaneously for the same destination, which some SD-WAN platforms do for load balancing, and both links have separate IPsec tunnels into Prisma Access, then the same session may have forward packets arriving on one tunnel and return packets arriving on the other. Since each tunnel terminates at a separate virtual interface in Prisma Access, this creates the asymmetric routing scenario we have discussed throughout this series. The solution is to configure SD-WAN traffic policies to use per session load balancing rather than per packet load balancing, ensuring that all packets belonging to a given session consistently use the same WAN link and therefore the same Prisma Access tunnel. Global Protect Gateway Selection Algorithms. Gateway selection is the process by which the Global Protect agent chooses which Prisma Access gateway to connect to when a user initiates a VPN session. This selection process has a direct impact on routing symmetry because the gateway a user connects to becomes the enforcement point for all of that user's sessions. If gateway selection is not stable and consistent, a user may connect to different gateways for different sessions, creating asymmetric routing for communications between those sessions. Prisma Access uses three gateway selection methods. The first is automatic, where the Global Protect agent connects to the gateway with the lowest measured latency at the time of connection. The agent sends probes to all configured gateways and selects the one that responds fastest. This is the default and generally the best method for pure performance optimization. However, It can cause instability if network conditions fluctuate. A user might connect to US East on Monday morning and to US West on Monday afternoon if latency measurements change, even though both gateways are reachable. The second method is priority-based selection, where administrators configure a priority order for gateways per user group or network location. Users in New York are configured to prefer US East gateway first and US West second. This provides predictability at the cost of some performance optimization, and it ensures that users consistently connect to the same regional gateway unless their primary gateway is completely unavailable. The third method is manual selection, where administrators define gateway assignment rules based on source IP ranges, geographic location data, or user attributes from the identity directory. This is the most precise method and is particularly useful in deployments where users at specific physical locations must consistently use a specific gateway for compliance, data sovereignty, or routing optimization reasons. From an asymmetric routing standpoint, priority-based or manual gateway selection is strongly preferred over pure automatic selection. When users consistently connect to the same gateway, the routing path for their sessions is predictable, the service connection used for their internal traffic is deterministic, and the enforcement instance that creates their session table entries is stable. All of these properties are essential for maintaining symmetric routing across the lifetime of user sessions. End-to-end flow. Branch-to-branch remote network to remote network. The branch-to-branch traffic flow is one of the more complex routing scenarios in Prisma Access because it involves two remote network tunnels, the internal Prisma Access backbone, and potentially the service connection if the branches are in different compute locations. Let us trace this flow carefully. In this scenario, a workstation at branch A at IP 172.16.1.50 needs to communicate with a server at branch B at IP 172.16.2.100. Both branches are connected to Prisma Access via remote network IPsec tunnels. Branch A is connected to the US East compute location and branch B is also connected to the US East compute location. This is the same region scenario. The workstation at branch A sends a packet destined for 172.16.2.100. The branch router forwards this packet through the IPsec tunnel to the US East remote network endpoint in Prisma Access. The packet arrives at the enforcement engine with source 172.16.1.50 in the remote network zone. The routing table lookup for 172.16.2.100 finds a route pointing to branch B's remote network tunnel, because branch B advertised 172.16.2.0/24 via BGP when its tunnel was established. The traffic steering policy is evaluated and the rule for remote network source to remote network destination allows the flow through the service connection or directly through the backbone, depending on configuration. A session table entry is created. The packet is forwarded through branch B's remote network tunnel to branch B's router and on to the server at 172.16.2.100. The server generates a response destined for 172.16.1.50. Branch B's router sends this response through its remote network tunnel back into Prisma Access. The enforcement engine looks up 172.16.1.50 and finds the return path pointing to branch A's remote network tunnel. Critically, it also matches the incoming return packet to the existing session table entry created for the forward packet. Because both branches are in the same compute location, the session table entry is visible to the enforcement instance handling both tunnels. The return packet is forwarded through branch A's tunnel to the workstation, and the session completes symmetrically. In the cross-compute location scenario, branch A in US East and branch B in Europe West, the routing path is different and more complex. The forward traffic from branch A must transit through the US East internal backbone, cross the Prisma Access inter-region fabric, and emerge at the Europe West enforcement instance before entering branch B's tunnel. The session table entry is created at the Europe West enforcement instance for the portion of the flow it handles. Return traffic from branch B re-enters at Europe West, matches the session entry there, crosses back through the inter-region fabric to US East, and exits through Branch Ace Tunnel. The inter-region fabric handles the session handoff between compute locations, but this only works correctly if cross-compute location ROT sharing is explicitly enabled in Panorama. High availability and failover routing behavior. High availability in Prisma Access is handled differently than in traditional on-premises firewall deployments. In a traditional deployment, you configure active-passive or active-active HA pairs with dedicated HA links and synchronized session tables. In Prisma Access, the HA architecture is abstracted away. Palo Alto manages redundancy within the cloud infrastructure on your behalf, but the service connection and remote network tunnel redundancy is something you must design explicitly. Within the Prisma Access service infrastructure, gateway redundancy is automatic. Multiple virtual instances of the Global Protect gateway run within each compute location, and if one instance fails, the Global Protect agent automatically reconnects to another instance. The new instance does not have the session state from the failed instance, so existing sessions will break and must be re-established. For TCP applications, this typically means a brief connectivity disruption of a few seconds while the TCP stack retries. For long-lived connections like SSH or database connections, the disruption may be more significant. For the service connection, redundancy is achieved by configuring two IPsec tunnels to the same or different corporate border routers. BGP runs over both tunnels, and the primary tunnel uses a higher local preference value so that routes received from it are preferred over routes from the secondary tunnel. When the primary tunnel fails, the IKE dead peer detection mechanism detects the failure within the configured timeout period, typically 30 seconds with a 10-second interval and 3 retries. The primary BGP session then goes down, its routes are withdrawn, and the secondary BGP session's routes become the best path. Traffic reconverges to the secondary tunnel. The routing implication of this failover is important to understand. During the reconvergence period between when the primary tunnel fails and when the secondary tunnel's BGP routes are fully propagated, some traffic will be black-holed. Sessions that were active during the failover will experience a disruption. After reconvergence, new sessions establish correctly through the secondary tunnel. However, sessions that were established through the primary tunnel had their session table entries created on the primary enforcement instance. When those sessions return, traffic now arrives through the secondary tunnel at a different enforcement instance. The return packets will not match any session entry and will be dropped. This is an unavoidable consequence of failover. It is a one-time asymmetry event, not a persistent routing design flaw. Users must re-establish their affected sessions after a service connection failover. Series summary and what comes next. We have now covered a comprehensive foundation of Prisma Access architecture, routing design, and asymmetric routing resolution across 30 slides. Let us summarize the key takeaways and outline what will be covered in the continuation of this series. The fundamental principle that governs everything we have discussed is that stateful security enforcement requires symmetric routing. Every design decision in Prisma Access, from BGP advertisement strategy to traffic steering policy to gateway selection, ultimately serves the goal of ensuring that both the forward and return packets of every session pass through the same enforcement instance. When this condition is met, Prisma Access operates flawlessly. When it is violated, sessions drop and users experience connectivity failures. The three most powerful tools for achieving symmetric routing in Prisma Access are: first, routing preference, which provides deterministic policy-based path assignment that overrides BGP ambiguity. Second, traffic steering policy, which enforces consistent forwarding rules for every class of traffic. And third, precise BGP advertisement discipline, which ensures that the routing table on both sides of the service connection accurately reflects the actual reachability of every prefix. Apply all three in combination and you eliminate the vast majority of asymmetric routing scenarios. The three most common mistakes that produce asymmetric routing in production deployments are: first, deploying remote networks and service connections in different compute locations without enabling cross-region route sharing. Second, using overly broad summary routes in BGP advertisements that include prefixes not actually reachable through that specific path. And third, failing to advertise mobile user IP pool prefixes from Prisma access back to the corporate network and to branch remote networks, which breaks the return path for sessions to mobile users. In the next part of this series, we will go deeper into advanced topics including Prisma access integration with Palo Alto Cortex Data Lake for logging and analytics, the use of explicit proxy mode for environments where agent installation is not possible, Prisma access for networks configuration for large-scale enterprise SD-WAN deployments, and the detailed configuration of custom certificates and PKI for IKEv2 authentication. Thank you for your attendance. Please consider subscribing to the channel and liking this video.